Example 6 asks us to evaluate the definite integral from 0 to 1 of the square root of x minus x squared. This is another example where we're going to need to complete the square. So I'm going to rewrite the radicand. So we have negative x squared plus x. What I'm going to do is I'm going to factor out the negative 1. So we get x squared minus x. And if you followed along in the previous video, what we're doing is we're completing the square. So I need to take the b value, which in this case is negative 1. I'm going to divide it by 2, and then I'm going to square that. And if I square negative 1/2, that gives me 1/4. So inside of my parentheses, what's happening is I'm going to end up adding 1/4. And then because I factored out the negative 1, if I distribute this back in, I subtracted 1/4. So on the outside of my parentheses, I need to add 1/4. And so now what I can do is I can factor the thing inside the parentheses. So this is going to factor into x minus 1/2 quantity squared plus 1/4. And then just so that this matches in my table of trig substitutions, I'm going to rearrange this. So this becomes 1/4 minus x minus 1/2 squared. And this is of the form, if you look at our trig sub table, this is of the form a squared minus x squared, or a squared minus some variable squared. Now our variable just happens to be x minus 1/2. So we're going to go ahead and utilize that as we're trying to figure out what trig substitution we need to do. Okay, so looking at our trig subtable, when we have a squared minus a variable squared, we're going to let x minus 1/2, because that's what's right here, and we're going to let that equal our a value, which in this case, our a value is 1/2, because notice that 1/2 times 1/2, or 1/2 squared, is what gives us 1/4. So x minus 1/2 we're going to let equal to 1/2 and then sine of theta. And if we take the derivative, we get dx is equal to 1/2 cosine of theta d theta. So now we're going to rewrite our integral, and we have, notice here, because we're substituting in stuff in terms of theta, I can't rewrite my original limits of integration for my definite integral. So in this scenario, why don't we solve for new limits of integration? So I'm going to use this equation to solve for my new limits of integration. So if my original lower limit was x equals 0, then I'm going to get 0 minus 1/2 is equal to 1/2 sine of theta. And then 0 minus 1/2 is just negative 1/2. Then from here, I can multiply both sides of the equation by 2. So I get negative 1 equals sine of theta. And because we're thinking about the domain here, looking back at our table, remember that we set the domain for this case to be between negative pi over 2 and positive pi over 2. So the solution to this on our restricted domain is theta equals negative pi over 2. So coming back over here, my new lower limit of integration is negative pi over 2. And then let's now work with our old upper limit of integration, which is x equals 1. So I have 1 minus 1/2 is equal to 1/2 sine of theta. I want to solve for theta. So I get 1/2 equals 1/2 sine of theta. If I multiply both sides by 2, then I get 1 equals sine of theta. Keeping my domain in mind, I know that theta is equal to pi over 2. So pi over 2 is my new upper limit of integration. Okay, So now I have the square root of 1/4 minus 1/2 sine of theta quantity squared times, and then dx is going to get replaced with 1/2 cosine of theta d theta. Let's go ahead and square this quantity. So if I square that, that's going to give me 1/4 sine squared theta. And then both of my terms have a 1/4 in it. So now I'm going to go ahead and factor out 1/4. And then 1 minus sine squared theta, based off our Pythagorean identity, that is equal to cosine squared theta. And now I can go ahead and take the square root of that. So that's going to equal the definite integral from negative pi over 2 to pi over 2 of the square root of 1/4 times cosine squared theta, which is going to give me 1/2 cosine of theta. And then we have times 1/2 cosine of theta d theta. I'm going to go ahead and combine those. So 1/2 times 1/2 is 1/4. 1/4 is a constant, so I'm going to factor that outside of my integral. And then we have cosine squared theta d theta. So now my recommendation is to use the power lowering identity for cosine. Something else that we could recognize is cosine squared is an even function, and we're integrating right now from negative pi over 2 to positive pi over 2, or in other words, from negative a to positive a. So to make our life even easier, I can double the integral and change my lower limit of integration from 0 to pi over 2. So 2 times 1/4 is 1/2. So I'll just rewrite that as 1/2. And then cosine squared theta d theta, we said earlier cosine squared theta is an even function. So that's why we're able to do this. We're using properties of symmetry. And now I'm going to rewrite cosine squared theta using the power lowering identity. So that's equal to 1/2, which I'm going to factor out that 1/2 outside of my integral. And then we're left with 1 plus cosine of 2 theta d theta. So that's equal to 1/4 times the integral from 0 to pi over 2 of 1 plus cosine of 2 theta d theta. Now I'm going to go ahead and start to integrate. This is going to give me 1/4 times the antiderivative of 1, in this case is theta. And then, let's see, I'm going to have plus 1/2 sine of 2 theta. And this is a definite integral, and our new limits of integration are from theta equals 0 to theta equals pi over 2. And since we solve for new limits of integration, we don't have to switch back to be in terms of x, although if you didn't solve for new limits of integration, you absolutely could go back and change things back to be in terms of x. Okay, so let's go ahead and plug in our limits of integration. We have 1/4 times theta is pi over 2 plus 1/2 sine of 2 times pi over 2 will just be pi, minus 0 plus 1/2 sine of 0. Let's see. So sine of pi is 0, sine of 0 is 0. So it looks like we're going to have 1/4 times just pi over 2. And so our final answer here is pi over 8.